right, guys. We're gonna give everyone a few more moments, and then we'll be good to go. Go ahead and pop out the chat. All right, well, it is currently 5 o'clock my time, so let's get started. So today is the second to last lesson for vision, and now we're going to get into a bit more fun. So first we're going to talk about pose detection, keypoint regression for multiple key points, and then we're going to take a look at object detection. And then we're going to look at some multimodal models based off of the new Kaggle competition. So a few updates with the library since last time. fastai2 now works with the new PyTorch version, so we no longer have to mandate our sizes. You can just run this fine. The only thing is comment that out. But besides that, let's get started. So what is keypoint and pose detection? So with keypoints, you want to try to find either specific joints or a specific position on a person. And we can do this through just simple regression, where we pass an n, where our n is going to be the number of key points that we have times 2. And the reason for that is we're really regressing, if we're looking at 7 key points, 14 separate values. So let's go through and look at the data set for today. We're going to be using the cats data set on Kaggle. And basically, it's a data set where you have these labels that point to various positions on a cat's face. Very simple problem. And it's just something to kind of show how we can go about doing it, what the concept is. This in real models that have been published, most of the time they work on a subset of COCO, where they either have one human or they have multiple people in the frames, and they work with those key points. Now we're going to use Google Down to download the data set because I'm storing it myself in Google Drive, and so this will let you just download it right away. And part of the lesson for today is going to be cleaning your data sets and how to tell when something's a bit wrong and how you go about fixing that. So let's take a look here. It's Kaggle. Should we trust it? Let's look at how it's stored. So if we extract our newly downloaded zip file and take a look through the folders, we can see that we have a main cats folder, and then cat 5, 6, 1, 2, 3, 4, and 0. All right. Well, those are actually all duplicates. And so the first thing we're going to do is remove the duplicates from it. And so really, we're downloading the same data set twice. So after we've removed everything, we're going to move all of the files in each separate individual folder up one level. So that way we don't have cat 1, cat 2. It's all just there. Because we don't care about classifying the cats. We care about specifically just what the points on the cat are. So now if we take a look at how they're labeled, and it shows here as well, the annotation data is stored in a file with the name of the corresponding image plus a .cat at the end. And there's one annotation for every single image. So to get our images, first, we'll just do get image files. And then to get our list of labels, we'll go ahead and just do a get files that searches specifically for the .cat extension. Get image files calls get files and just passes in an image extension instead. And now we just want to make sure that we have the same number of labels and images. If you grab it rawly from the Kaggle, you'll notice that that's different. So there's a lot of cleaning to this data set. It's not very well maintained, at least initially. So now ideally, we should all be okay, right? We have a label for every cat image. Let's make sure of that. So the first bit is we want to make a image name to keypoints file that will go through and return to us the file with our keypoints. We're going to use the first image as an example, which is this beautiful little kitty right here. So to get the coordinates, we're going to use NumPy to generate a NumPy array from a text file, what our text file is. And so we can pass in a file name to our image to key points. And now we have this array. But that doesn't quite look like key points to you, does it? Because sure, this could be an X and this could be a Y, but what the heck does this 9 mean? Well, let's go back to the Kaggle website, and under content, it actually says and describes what all is going on. So the order is first the number of points present, followed by the left eye, the right eye, mouth, left ear, right ear, and then it just continues on from there. With the left ear 1, right ear 2, each point on the ear has a separate individual point. So the ears have 3 points in total for 2 ears. Now we need to separate these into pairs because right now they're just a giant list. This is what our separate points function is going to do. So it's going to take a bunch of coordinates and then go through and group them together as a tensor. And now we need to merge all that back together through some sort of a getY function for us to work with tensor points, which is what all of our points are going to be. So we'll go ahead and load that into a getY that calls from a path and returns some points. And so we've made sure that at the very least, all of our images have associated key points with them. Great. Is there anything else I have to watch out for with these kind of data sets? Well, what if, per se, the person that was building the data set decided to label some images even though the labels weren't per se in the visible region? That's exactly what happened to this data set in particular. And so we need to figure out a way to go through and test all of our images and make sure A, that they open, and B, if they do open, make sure that all of our points are within the visible range. And if any aren't, then we're going to go ahead and set that away as a removal. And so that's what this little algorithm here does for us. So it's going to check and make sure that our X is less than our X. And if it isn't, then go ahead and add that to our bad file names. Check the Y. And then if anything else isn't true, go ahead and add it to our bad images. And if we take a look, we have another 1,400 images that are going to mess our data pretty badly. And the reason for this is, and I say mess up, you can train a model on the raw data, but you need to understand what it's going to be looking for. So in the context of this particular problem, if let's say this is my image, but the only part of the image that we saw was, say, everything right in there. What's going to wind up happening is we have a label for these points up here. And if I pass that in, while there might not be any visual cues, one moment. There we go. While there might not be any visual cues that we might have a point there, the model can actually discern that because we're physically telling it there is a Y there every time we generate some points. So to that regard, if you want a model like this, then you don't have to go through and clean it. But we don't. We just want a model that will go through and actually just get the 9 points based off of realistic images. So afterwards, we are basically we have 3 options essentially with these bad images. So now let's make sure that we don't have any repeat names. And so we can do that by generating a set. And in total, we have about 1,000 more images. So again, as I said earlier, we have a few different ways of tackling this problem. The first is we just remove that particular image entirely and don't even worry about it. The second option is to zero those points to -1, -1. And now the model will basically default to, if something is not there, then we'll say go to -1, -1. This is common in things like Cocoa, where if something isn't there, then it's defaulted to -1, -1. And you can adjust the loss function to take that into account. And then the last option is the technique that I mentioned earlier, where we just keep the points and we try and predict off the screen. So now we'll go ahead and clean up our images and go back to working with our tensor points. So this is just an example of kind of what we're going to be doing. So we're going to pass in an image and an array of points and return back a tensor point, and the size of the tensor point will be the image's size. And so this will keep track of how big our image is as we go through transforms. And so now we just have this 1/2 tensor that we'd expect. So let's go ahead and try visualizing it. Because remember, I said that they keep track of the size. So we're going to need to pass in the axes of our original image into our tensor points show function. And now we can visualize our 9 points for our cat. Now let's look at some DataBlock stuff, because the transforms get a bit tricky when it comes to dealing with these tensor points, because you don't necessarily want to just use them anywhere and anything. So the first thing we're going to talk about is clamping, and that was that transform that I mentioned, where if it goes off the screen, then just default it to -1, -1. It's the safest for, say, if we did something like a random resize crop and suddenly now it crops around a place that's no longer there. Well, the points that got cropped out will just zero. And so that's what this little clamp batch function will do. But otherwise, and we'll go ahead and include it, but we're going to use the transforms that don't affect anything with our Y's going off the screen. Now, for those trying to understand how to read this, remember encodes is how we get through to a target, not necessarily undoing the target. And so as we prepare our Y's, it passes through all these encodes. And so here we just say for every X, and this is a batch, so this is a batch transform. And then for every pair in our batch, clamp down to some minimum and maximum value. Here I just set the minimum to -1 and the maximum to 1. And if any of our values are above, go ahead and default it to -1, -1. Because when we're going through and normalizing this -1 to 1 scale, what that really means is starting at 0, what percent in a particular direction is my point. And so if we're at -0.5, it's halfway down to the left side of our image. Otherwise, we're going to want to use the squish or padding resize methods. If you pass in a resize, this will then just keep the aspect ratio and everything kind of similar. For the batch transforms, we can use flip, rotate, zoom, warp, and clamp batch. And then in total, I included a nice list of all of the keypoint arguments that are available. Now with random resize crop, remember to include it with clamp batch, otherwise you might get that point off of the image issue that we talked about. Otherwise, the data block is very straightforward. Image block, point block, because we're doing a point problem. Our get items, splitter, our get y that we generated earlier to get our target, and then just our transforms. Now, with any of these problems, before I even do a show batch lately, I'll do a summary and pass in whatever path or item I'm expected to be looking at. It's a great way to make sure that you're getting some Ys first, and then make sure if those Ys look accurate, and then show batch is kind of a final look at how your augmentation is doing. And so here we just pass in the folder that we expect everything to be in. It's in our base directory in Colab, so we can just go ahead and do the single quotes. And it'll go through and try and build a sample and come out with our final tensor point. Go ahead and try and build a batch. And then after it's tried to build a batch, it'll do 3 more. And then afterwards, as long as we don't have any issues that are explicitly stated here, we're done. And so now if we build our data loaders and show a batch, we can see that all of our key points relatively match up. If they don't, that's due to human error. That's not due to us. And so finally, we're going to want to give a .classes attribute or a .c to our data loader. That way CNN Learner and any other sort of helpful model technique can go ahead and create however many outputs we're going to need. Now for today and this lesson specifically, it's going to be a lot about creating more custom models working with the API instead of just going and letting it do its thing. Because ideally, after we have this dataloaders.c value, I can run CNN Learner, just pass in my data loader, the architecture I want to use, and I'm on my way. And that's it. But I want you guys to understand a bit more of what's going on. So we know our inputs, we know our outputs, and so we're going to go ahead and make a custom head again. So we're going to use the body of a ResNet 18, which I know, small model, but in this problem, it actually works very well. And it's even mentioned in the literature of a ResNet 18 versus a 34 because it is lightweight. And if we look at the very last block of our body, we'll see that our output is a 512. Now, every time we generate a head in fastai, we have 2 pooling layers. We have an adaptive average pooling and an adaptive max pooling. And so what that means is it's not the output goes through adaptive average and then adaptive max. The output goes to both of them at once. And so that's why even though our input was a 512, we're really expecting 1024 because it's going to be 2 of those layers. And then we're going to declare our outputs as those 18 total targets. And now we can just see our head. Now we can wrap this around in a sequential object and we can split it. So anytime you split your models, generally it's going to be indexing into it. And so first we want to make sure that we even can. That's why we wrapped everything in a sequential, because at 1 is going to be the head and at 0 is going to be the body. And this is just the default ResNet split that we're stealing for today. But in general, you're going to have M, which is your model. You're going to have whatever your indexes are that you want to split by. And then you need this map params every single time. And so now if we look, arch at 1 forward is just the head of our model. And then finally, we can initialize that last little bit, initialize those layers, and to a chiming normal. And now we're basically done. We can make our learner, pass in a splitter, use mean squared error as our loss function, and then we're going to use the ranger optimizer today. And now we can freeze like CNN Learner does, fit our model, and we don't really have any metrics here per se, because while we can keep track of each individual key point if we want to, it's usually better if you just keep track of the training and validation loss. There are certain instances where one might be better than the other. For say, if you're missing a few points and you want to keep track of those instances. I'm not sure if I have an example here, but I can show an example in the forums of how you'd build a custom metric to keep an eye on that. And if we look at some initial results, it's really not bad after just 5 epochs, especially with that small of a model. So we'll go ahead and unfreeze, train a bit more. And I know I'm probably going to get a lot of questions about how do I read this. So I just chose kind of 1e-neg4 because it's still declining, but somewhere in the middle. You know, I've said this before, it's more of an art than it is a science. Fit a few more times, And that model's pretty good. And that's really all there is to it. So we just trained a Keypoint model in about 10 epochs total on a very small architecture. And usually that takes a few hundred epochs or so, depending on how your augmentation is doing and other bits. So the main thing I want you guys to walk away with is in the fastai lectures, they show the head pose data set. And that's just one individual point. I wanted to give you guys an example of what does multiple points look like and show you kind of a few warnings with the transforms and how really it's not too different to just start with 1 point and go to, say, 7. So the next notebook we're going to look at is hybridizing models. And the whole point here is to kind of get your creative thinking. Last lesson, we used a U-Net, and we used segmentation for that. Now, what a U-Net is very good for is looking at individual pixels and individual clumps of our image and extracting a lot of information from that. And so we're going to try and apply that to a few places where it might be good and it might be bad. Specifically, the Keypoint Regression, multi-label classification, and the regular classification. Now, we're only going to go through the Keypoint Regression, which is going to be the exact same thing that we did last lesson. But the technique still works for the multi-label and the classification, and you can kind of see how those results came out. But this just prepares the data exactly like how we did before. And now we're going to get to the model. So FastAI's U-Net specifically generates from this U-Net learner function. And we're going to go through and try and see if we can understand where we need to adjust our model to give it this sort of custom head that we need to strap on for almost any task. And so if we follow along here, how I'm reading this is I'm looking for, okay, we have arch. Well, at some point, I call create body. All right, now if I'm passing my body into something, that means that it's probably going to generate a head of some degree. And so if we track where body lands to, we get models, U-Net, dynamic U-Net. And so here is what's really generating the head of my model and the rest of the U-Net. So we're going to try and adjust that ourselves to make it a more custom U-Net. Now this goes through and grabs the helper functions that U-Net learner is going to need. But the one line we're going to want to change first, eventually, will be this one, where instead of dynamic U-Net, we're going to call a custom U-Net. And the main bits that we're going to look at specifically here is we don't want to touch anything else except for that last layer right before really the output layer, because we can send in anything we want, and as long as we declare the right outputs, then no matter what, the model will train. Will it train well? It depends on the task, it depends on the model, but any model will train. So the specific layer we want to get rid of is this last conv layer that's being called, because this, you can see, calls our number of classes. So let's go through and try and generalize generating this output. Now create head needs whatever our last layer's output size is going to be. And so we can grab the number features model and actually just pass in one particular layer, and that'll get that one layer's output size. It's a very cool function because it'll actually adjust depending on how many channels it is, depending on if it's a linear layer, and find an X until an X fits. And then from there, it'll find your outputs. And so here we're going to call the last layer, and we're going to want two of those, remember, because we have two pooling layers. And so now we can, at the very end of our layers, do a create head, pass in our number of filters, our number of classes, and we're good to go. That's all there is to it, to just change that last layer. And now instead of using U-Net for segmentation, we're going to be using it for Keypoint Regression, Probably something that was not its original intent, but we're going to see if it works. And so now we're just going to make a custom UNet function that calls our custom UNet model. Otherwise, everything else is going to be pretty much the same. Pass in our model and a loss function. And then whenever I start adjusting these things, another nice way to make sure that you haven't broken anything before you start training is to call learn summary. Because learn summary will go ahead and just throw a batch through your model. And if you get a resize error, you're going to know it now before you already allocated all the memory for your batches, and suddenly you're out of memory errors, and it's a fight. Very, very nice to be able to just debug your model right here. So this just goes through and shows that at the very end, we have our custom head here with our 18-point output size. Now we can just find our learning rate. And we're going to fit for about 3 epochs, which I know might be very surprising, but let's take a look. So our very tail end loss function was around 0.005. In 3 epochs, we got 0.01, which actually was a few epochs less than what it took with just the standard ResNet. Now, part of that could be the ResNet backbone that was a little bit bigger, but in any case, the model fit in a considerable amount of less epochs and got pretty decent results, especially on, like, say, a hard image right here. So it's a creative example, and kind of to show you guys, don't be afraid to think outside the box when it comes to these models. Now, there are drawbacks to everything. This is a bigger model, so you're going to be working with lower batch sizes. Like if you noticed, if we went back to when we made the data bunch, my batch size was only 16, whereas we had 34 or 32 or 64 the last time. So everything has a cost, but just keep that in mind. Otherwise, I have a few examples of applying our custom UNet to classification and multi-label and showing how it does. The results are fairly close to how the standard ResNet did and how the standard notebooks do. But again, focus more on the technique and the idea rather than per se the results, because every idea is at least worth a try. And so now let's move on to object detection. So well, first, was there any questions about any of the Keypoint mumbo jumbo I just went through? I am muted. Okay. Let's run through that again.
For how long?
Bad. Thanks for the heads up. All right, so object detection, where we find localized areas to where a particular object or class is in the image. Now, for us, I've provided some support classes and files for you to use instead of building the model ourselves, because I want to focus more on the technique rather than the theory. So we're going to use the same one that Jeremy used a few years back in his Part 2 lecture. But let's get started. So the data set is going to be the Pascal data set. And the thing with bounding boxes is most of the time the label comes in a Cocoa style JSON. And fastai has a very, very nice get annotations function that'll go through and read a JSON file and extract the image names along with their label bounding boxes. So we'll go ahead and call this on our training JSON file. And if we look at the first image and the first bounding box label, we see the 4 coordinate, or the 4 points, which correlate to the bottom left and the top right, along with the particular class. Now, in order to access that quickly, we're going to go ahead and make an image to bounding box function that'll go through and search any particular image name for the associated bounding boxes in the photo. And so just to make sure everything is all working, this little technique here, it's a little Python, I wouldn't say shortcode because it's very complex, but it's a way for you to check the first item in your dictionary and make sure everything is looking okay. And so here we're going to pass in the first file name of 12, and we can see its outputted coordinates along with that car that we saw just a second ago. So from here, we're going to want to make some getters to get our x's and y's. Now here's one of the first instances of a model where we have multiple outputs, where one model is going to output a classification along with a point regression. And so we're going to want 3 getters essentially. The first one is just going to be a lambda function where we're going to pass in a file name, and it's going to grab that file. And the other 2 are going to search for that file name's bounding box along with the labels associated with it. Now, from there, we can just go ahead and use the item and batch transforms that we defined earlier for the keypoint problem, because this is still keypoints. And then finally, we're going to use, we need to get our items somehow. And the thing is, we already know what they are, and we don't need to declare them here necessarily. And so all we're going to do is make what's called a noop function, which noop says no matter what my input is, ignore it, or no matter what you want that variable to be, ignore it, and just do whatever. And so in our case, don't care about the input, it's just going to return our list of images. And so now we're going to build our Pascal data block, where we're going to have an input of an image block and an output of a bounding box block along with a bounding box label block. Please say that 3 times fast. A splitter that we want to split our items into, our custom get items, which is going to be get train images, our getters, which is the 3 that we defined earlier, our item transforms, our batch transforms, and then the last thing we want to do is declare the number of inputs we want. And so what this will do is if we say had 2 x's, then we would say 2, and what that's going to do is say that this one and this one are going to be our inputs. Otherwise, everything else is going to be our y's. And then finally, we can make our data loaders. The last thing we need to do is assign it with some classes. There's 20 for this particular data set. And so we can look at a batch. And it's just like you'd expect. We have bounding boxes around our images. We made everything right. For the architecture, we're going to use a particular one called RetinaNet. It is the one that Jeremy lectured on in the Part 2. I'll go ahead and put a link after this lesson in our study group. That way you guys can all go watch the lesson if you want to learn more about the theory behind it and a bit more about the architecture. But otherwise, go ahead and you can clone my repository and work out of the imports. And so the first thing we're going to want is RetinaNet is built exactly like everything else, where we have some sort of an encoder similar to how the rest of our models are. So here we're going to use just a simple ResNet 34, and we're going to grab our number of classes and pass that into the call to RetinaNet. Now the final bias here, Jeremy has his example, honestly, at -4, and most of the time with Jeremy's examples, they're pretty good. Are the image rotated because of augmentation? Yes. If we go back to our augments right here, you can see that we have rotate and flip. And so now we're going to try and take a look at what this RetinaNet is really making. Because ideally, now we're going to kind of make multiple heads for one model, because this one particular model is going to output 2 to 3 different values. And so if we look at our first example, we just have one head that has a last linear layer that outputs 4 features. Well, here we have 3, a smoother, a classifier, and a box regressor. And so if we look at our smoothing layer, it's a whole bunch of convolutional 2Ds. If we look at our classifier, it's still some convolutional layers. And then our box regressor is also convolutional layers. So there is no linear layer here. And the reason for that is all of the extraction of those key points and those labels happen in the forward function of our model. And if we go look at the actual model itself, I'll go through ahead and we can look at that very briefly, because we are running a little bit ahead of schedule. Specifically, I want to look at the forward function of it. We can tell that we're getting multiple outputs because we're returning an array here, where we're applying we're sending in some input to a particular head, so our classifier and a box regressor, along with some states here. So that's just one way that you can get multiple outputs out of your model. That's ideally the way that you'd want to, but you also have to think about what you're expecting your model to do. We'll look at another example of multiple outputs after this one. Otherwise, for the loss function, for bounding box and object detection in general, you need to have what's called ratios and aspect ratios and the scales that our images should be. The paper used 1, 2 1/3, and 2 2/3, but that was also a much larger image size. And for us, that would go way out of the box. And so we're going to go ahead and scale those down. Now, when it's bolded, that's because that should be 2 to the power, just like it's written here. And then we're going to use a loss function specifically designed for RetinaNet called RetinaNet Focal Loss. And we can make our learner. So we're going to make another split here because it is kind of a pre-trained model. And we're going to separate it into our encoder and then everything else. And so here's one way to do it. We have our M encoder, and since we can't necessarily index into our model because the specific heads are at specific regions, instead we can just call them. And so we have our top 6, top 7, merge layers, smooth, classify, and box regressor. So now we pass in our loss function and that splitter, freeze, and now we have our learner all geared to go for object detection. And as you can see, it's a very big model. So now we can find a learning rate, which here we want about 1e-4, and then you can go ahead and fit for a while. I guess it cut off after I trained, but That's how you do object detection. Now, keep an eye on this notebook. I didn't have time to get to it yet, but the inference for it can be a little tricky. You can start to see the code that I was working with in the imports. I believe I have an evaluation or a predict script. I'll go ahead and update this notebook later with that working once I get to there, unless one of you beat me to it, but it'll be there. So besides that, let's go, are there any other questions first before we switch topic one last time? All right, in that case, time for some multimodal learning. So we're going to be taking a look at the Bengali AI competition, and specifically it's a Kaggle competition about classifying handwritten digits. Now, I'm not going to describe a winning solution or anything. I just want to show you guys the general idea, and this data set just happened to be a very, very good example for doing so. So it will help you get started, but I can't promise that you'll do good because it's a very simplistic example. So this assumes that you have downloaded the data for this competition and have stored it away in some sort of Bengali AI zip file. So the goal for this competition is we're given one image of a handwritten character, and we need to extract 3 different outputs from it: the root, the vowel, and the consonant diacritics. So let's go through and kind of look at how we do that. The first issue with this is all of our data is stored away in the CSV file. There is no image files. It's really in these parquets. And so we need to go through and generate it. But if you're like me, I have no idea how to even work a parquet. Well, the nice thing about Kaggle is most of the time, if you go look into the notebooks, there's usually a very helpful notebook somewhere along the line where someone has helped get us started with preprocessing. In this case, we have a notebook right here for generating 128 by 128 images. And so we're gonna base it off of his example. So we're going to go through and open all of our parquet files and attempt to basically clean up the data a bit. And how we do that is we're going to first build some bounding boxes and do sort of a crop resize to where the items are being present at. And so after running this algorithm, you can see that our original image now is a nice and clean center image with our particular characters that we're going to be looking at. So from here, we want to generate the full data set and store it away in some sort of a zip file. And the one thing that I'll say is different with this competition is it's not 3D images. These are 2D. And so as a result, we're going to want to keep track of the mean and standard deviation. Now, we don't necessarily have to because of something I'll mention in a little bit. Well, yeah, I was there. We use Learner. So one thing that CNN Learner will actually do now is if you're going through and building your model and you accidentally forgot to include normalize, CNN Learner will include it for you along with UNet. And so you don't have to worry about accidentally forgetting to normalize everything. You're good. All right, sorry about that. They were running away to a Cyber Club meeting. So we're going to want to use the data set's actual mean and standard deviation. And so let's go through and look at how to build our data block. So we're going to go through and extract our newly made data set. And we're also going to make use of the fastai2 library, which for those of you that follow me on Twitter, you got a little peek at what this was going to be. But it's a cool way for us to visualize our neural nets. And our particular images are labeled in this training file, where we have the image ID, the root diacritic, consonant diacritic, and the actual grapheme. Now we just care about the 3. And so the first thing we're going to want to do is make sure that we get the total possible outcomes to build our head with. This can be good pre-processing for 2 different ways, because if we're, say, doing, say we're doing stratified k-fold, and we're dealing with a particular data set that doesn't have that many instances of a particular class, we can ensure that it's built to how the test data set will perform. Now, we don't expect it to be good on the actual problem if that missing image shows up, but we can still train it. And so we'll go ahead and make vocabularies for our grapheme, our vowel, and our consonant. And now we can build our data blocks. So here we're going to add one more block onto the list, essentially. So we're going to expect an image block that has a black and white image, and 3 category blocks where we're going to pass in the vocabulary we want it to use. And now we're going to need our 4 getters, which all of these will be column readers. And finally, our transforms. So we're going to go ahead and do aug transformations, random augmentation essentially, along with normalize from those statistics that we made earlier. And now that we have everything together, we can build our data block and again have our number of inputs to 1. And for this particular data set, because it's so big and takes so long to train, we're going to train a very, very small sample of it, just 1,000. That way it's something doable in the time. And so if we show a batch just to make sure everything's working fine, we can see that we have our image and our 3 individual labels. Now let's get through to our heads, because essentially we're going to have one model that does 3 tasks together. And so the first thing we're going to want is to create our body of our model, and we're going to use a pre-trained ResNet. But the big issue here is the ResNet was designed for a 3-channel image. And so we need to update that first layer in the body, or that first convolutional layer, to accept a single channel. And so this little quick function will go ahead and do it. This is just how I chose to do it, where we keep the weight still and everything is carried over. There's a few different ways that you can actually do it, but this is just one example. Might not be the best, but it's also not the worst. And now we're going to go through and focus on the head. So these are just some helper functions using the fastai2 library to basically visualize what we want our head to be. I won't go over this per se. It's kind of self-explanatory, especially whenever you go through and look at the examples in the documentation. But this is the type of model head that we're going to be building. So we're going to start with this convolutional 2D and then build 3 separate ones that will have a 168, 11, and a 7, and then a model output for all 3 of them. And we'll just make it super simple and call it multimodal. So our multimodal is going to have some sort of a body that we're going to want to get the number of output features for. And then we're going to create 3 heads. And how we wind up adjusting our model is in the forward function, where we just say, okay, get the output from my body, and then send this y through our 3 heads, and then just return them. So it's really very straightforward. There's not much fancy work to be done. But it's a cool little technique that we'll see actually works pretty good. And so now just to build our model, we pass in the body along with our classes. For training, we're going to borrow from Miguel Pinto's notebook. I've linked it there, but basically we're going to have a combination loss that's going to work with a basic cross-entropy loss, but has some weights associated with this. And then we're also going to have some recall metrics that focus on the previous few predictions. And now finally, we can make our learner. Now, I didn't go through and split the model here, but if we recall from the object detection notebook, you'd want to do something similar to our RetinaNet split, where you would do self.body and then grapheme, vowel, and constant as your other 3, basically, as your other 3 group. Other 3 layers as your one group. There we go. And so now we can go ahead and fit for a few epochs just to make sure everything's working. And you can see that even with such a small sample, we still clock in at 2 minutes and 20 seconds. So training these sort of models takes a lot of time, but it's in particular this data set. That's not necessarily for everything. But that's the lesson that I have for you guys today. We went over a few cool techniques. I'm kind of excited for the sort of ideas that you come up with for this multimodal technique and idea. I was trying to come up with a few data sets that you could work with, because it really is a cool technique that could be applied in a few places. But the best I was coming up with was a multi-classifier for, say, genus, species, family of some species, or a picture of an animal. But if you guys have some other ideas for this, I'd love to hear about it, and I'd love to see you guys build some models that do this multimodal sort of classification or regression. But otherwise, that's all I have for this lesson. Next week, we're going to go into audio, showcase a quick GAN notebook, and look at Siamese, and then that's going to be it for the vision block. So after that, we're going to get into my favorite part, which is the tabular. But thank you guys for joining me. If there's not any more questions, then I'll go ahead and end the stream. Thanks for watching.